Hello everybody, I'm here at home doing this lesson with my faithful dog Andy, who may or may not be very interested. Looks like she's not. We're going to talk today about how stars die. Okay, so I have a scanned version of this whole thing already done, but I'm going to do another one here and tell you fascinating stories. Alright, and I'm going to try to keep this under 20 minutes. It's going to be tough, but here we go. Okay, first of all, look at the front of the handout I gave everybody. Look at how big the sun is there compared to these famous stars in our neighborhood. Okay, look at the size of Betelgeuse. The red one. Look at the size of that thing compared to the sun. Okay. These other stars, some of them you've heard of on the HR diagram. 3 of them you didn't. You've never heard of that one, Adhara, Achernar, or Castor A. It's called Castor A because it's a part of a double star. There's also Castor B. Okay? There's Aldebaran, Fomalhaut, Capella. So on Friday's quiz, I can ask you technical questions about these stars other than the 3 that I just put check marks on. Okay. Oh, and by the way, Antares is even bigger than Betelgeuse. It's ginormous. They're not the biggest stars in the universe, but Betelgeuse and Antares are some of the biggest stars in our neighborhood. Sorry, I'm hand holding this because I don't have a camera stand at home. So every once in a while, my finger blinks in front of it like that, but I apologize. All right, here we go. You'll hear people say the bigger they are, the harder they fall. Okay? And the reason I'm mentioning that is how stars die. A star's death, its type of death, is determined by how massive it is, how heavy it is. How stars die. All right. Now, a star's mass determines the type of death it'll have. A star's... I'm leaving out words. I'm worried about dropping the camera. A star's mass determines the type of death it'll have. There are 3 different ways that stars die, and they're all spectacular. A star's mass determines the type of death it will have. All right. Let me pause for a second. All right, I'm back. So what I've done is I've drawn 3 columns for the 3 different types of death. Okay. And the first mass class, the one we worry about first, is the ones for stars that are only 40% of the mass of the sun. That's what that means. 0.4 mass of the sun up to 8 times heavier than the mass of the sun. Remember, humans compare all stars to the one we know the most about, our local star, the sun. Okay? All right. So the first thing that happens in this long death story is it begins running out of its favorite fuel, hydrogen. Begins running out of H. Be careful so you don't screw up hydrogen and helium. I've had students keep getting those 2 mixed up because they both start with H. Hydrogen is the number 1 fuel, okay? And it turns hydrogen into helium. That's what the job of a star is, okay? Now, I didn't say it ran out of H. I said it's beginning to run out of H, which means think about a campfire. If you haven't thrown a log on it for a long time, eventually the fire starts to cool down and it's getting dimmer and redder, okay? The same thing's happening to a star. Even though it's not combustion, when it begins running out of hydrogen, the temperature is going to start to drop. Okay? And then the battle between gravity squeezing the star and the inside heat and pressure of the star trying to make it blow up, the balance is thrown off. So now gravity is stronger and it begins to crush the star. So gravity collapses the star. Then something interesting happens. The star's core starts to heat up because it's getting squeezed harder, and that makes the temperature go back up. So the core temp goes back up. And so now you've got a star that's going to start being cooler than it was before. It was yellow. Now it's cooler So if you add a little bit of red to yellow, you get orange. Okay, so you would see this formerly yellow star, yellow dwarf, is now turning into a red giant. Okay, now for the stories I'm telling you today, anytime there's an event or an object formed that you could see, I'm just going to circle it. So we just made a red giant. I'm going to circle that. Okay. All right. Next, it's having problems. It runs out of hydrogen. It does not instantly die. Just because you've missed a meal doesn't mean you die. Okay. It will now switch to helium, which it doesn't want to do. Okay. It's been making helium its entire main sequence life. Runs. See, I'm leaving out words. Runs out of hydrogen. Sorry about that. So it's going to switch to helium. I'm going to put an exclamation point there. The star is not happy. It switches to fusing helium. Switches to helium. And we can see when a star does that. Okay? It's called helium flash. Because all of a sudden, a red giant star will suddenly get brighter. And we'll know, oh, that star's having problems. Okay, helium flash. Then, when it runs out of helium, it doesn't die. It switches to some of the other atoms it's been making. It runs more and more poorly each time it has to switch. It's like me trying to run on Brussels sprouts or asparagus or something else disgusting that I would, if I was running out of the food I liked, I would switch to stuff I didn't like. Okay, so the fuels, it might be running on carbon or neon or oxygen, something weird like that. Okay, switches to other elements. Switches to other elements. It's not enjoying life anymore. Switches to other elements. Finally, it runs into, it doesn't have any more things that can fuse. And fusion stops, and that deserves some exclamation points because that's what a star's job is, fusion. And what I want you to think about, this is disgusting and kind of graphic. Think about two people locked in an arm wrestling match and they're exactly even strength. So this match is going on for a while. The reason I'm telling you about having you visualize an evenly matched arm wrestling match is during the main sequence part of this star's life, gravity and the explosion force inside the sun have been balanced. Now, the inside forces pushing out so it suddenly stopped. And gravity thinks, I've got you now, and crushes the star. Gravity crushes. This is going to be very violent. Okay? The opposite of an explosion is an implosion. And that's what we just have happen now. This massive red giant star implodes. Then we have something called a nova happen. It's based on a word people did when back in the day when people would see a nova in the sky, they didn't know it was an old star dying. They said, oh look, there's a new star. And there wasn't a star there before. And for a few days or a few weeks that it's there and it fades away and they're, wonder what that's all about. That new star's gone. They don't know what they've just witnessed. Okay? I'll show you, I'll show you with some pictures off the internet of what that looks like. Okay? Now I'm going to draw a little dot here. That's the star. Okay? And here, I circled nova because you can see a nova happen. Okay? They're a neat event for astronomy nerds to witness. Okay? This is the star's outer layers. It's most of its guts blowing out into space. And it looks really cool. It's one of my favorite things to look at. Okay? All right. Tell yourself that is called a planetary nebula. It's not named correctly. When we first found these with telescopes, they're fuzzy and they look sort of like a planet, like Uranus or Neptune. Somebody thought, is that a planet? No, it's not. But the name has stuck. Planetary nebula. And that is a white dwarf. It wasn't a white dwarf before, but it's a white dwarf now. A hot little star. Okay? Here's some of the magic. When that star imploded, a small supply of brand new hydrogen was made in the implosion. And that new little star, remade little star, can go for a really long time, millions and millions of years maybe, on its new hydrogen fuel supply, because small stars are much more efficient than great big gas guzzler giant stars. Okay, so what happens at the end here is this white dwarf will cools and dims eventually, fades away, and scientists think maybe, we've never seen one, I don't know if we ever will, they think maybe there'd be a crystallized carbon about the size of the Earth left over. And you know what you call crystallized carbon? Diamond. Okay, anyway, cools and dims and crystallizes, we think. It wouldn't give off light anymore. It's a dead star. That's just really cool. Okay, all right. Now, if you think, boy, that's 11 minutes already. How's he going to tell us 2 more stories and get this done in 20 minutes? Watch me. Okay, now, this was the lightweights. These are heavyweights, and these are super heavyweights over here. Okay, the heavyweight stars are 8 times the mass of the sun, up to 25 times the mass of the sun. That's big. Okay, and many of the same things are going to happen. The problems start with running out of hydrogen, and the temperature dropping, and gravity collapsing, and the core temperature going back up. I can't tell you that it's a red giant because it's bigger than a red giant. It's a red supergiant, which we talked about. Okay? And it runs out of hydrogen, and it switches to helium, and it has multiple helium flashes. Those are complicated. I'm giving you a very generalized version of this. And it switches to other elements like carbon or neon or oxygen or silicon. Okay? It doesn't like it. And then fusion finally stops. That's really, really bad. And gravity crushes it. And it implodes. But the explosion that happens next, because when it implodes, then it explodes. Like all those atoms came crashing in, and when they all hit in the implosion, they bounce back outwards as an explosion. So here we are. What would be bigger than a nova? A supernova. I'm going to circle that. Okay. Now, the bigger they are, the harder they fall. The bigger they are, the worse the explosion when they go boom. Okay. So watch what happens here. This is one of the biggest explosions in the universe. One of. Okay. And it's so violent, it's able to actually rip the atoms apart. And atoms are some of the strongest things in the universe. The things that hold them together. Rips atoms apart. And there's a lot of atoms in a star. Rips atoms apart, exclamation point. If you remember from earlier grades, 8th grade for sure last year, the 3 ingredients of an atom, protons, neutrons, and electrons. Okay? The protons are positive, the electrons are negative, the neutrons are neutral. Okay? The 2 light ones, the protons and the electrons, are light and they are blown away. And they're not coming back. Protons and electrons are blown away. But what about the neutrons? Yeah. Heavy things don't go as far. If I gave you a golf ball, softball, and a bowling ball all at the same time, and you're like trying to hold on to 3 things, I said, now throw them all at once. The bowling ball wouldn't go as far as the golf ball or the softball. Okay? The neutrons are heavy. So the neutrons are pulled back by good old gravity again. Gravity is going to be a major part of tomorrow's quiz. Neutrons are pulled back by gravity. And they're all going to meet, have like a family reunion right where the star used to be. and they come screaming back in. They're being pulled back in. They went a long way out, but they came back in. They come falling back in, and they hit really, really hard, and there's no proton or electron drama getting in the way, with positive charges repelling other positives and negatives repelling other negatives and positives being attracted to negatives. Those guys are gone, and all the neutrals are brought back in, and we form something called a neutron star, which is one of the weirder cats in the universe. Very, very, very dense. The astronomy textbooks will talk about a tablespoon scooped out of a neutron star would weigh as much as a mountain. That's some pretty serious density. Okay, so I'm going to put a star around that. And I'm going to tell you a funny story, true story about aliens. A true story about aliens. When scientists accidentally found the first neutron star, they didn't know what they had found. They detected with a radio telescope an incredibly precise, fast, on-off, 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 on-off radio signal that they assumed was made by intelligent life. And they went to the government in secret and said, "We just found aliens. Do you want us to tell the public or not?" And the government wisely said, have somebody check your work before you go telling everybody we found aliens. And somebody else checked their work and said, "Sorry, boys, girls, whoever, you didn't find aliens, but you did discover a new thing, a neutron star." It was a ball of neutrons spinning very, very quickly, many times a second, and generating ferocious magnetism and radio waves, and they were detecting that. And you think, radio waves? Yeah, radio's not that weird. Lightning makes radio. So we've just done the heavyweights, how they die. Okay? All right, now, what about the last one? I've got 3 minutes left. I'll bet I can do it. The heaviest ones are greater than 25 times the mass of Sol. And many of these things are going to be the same. I'm going to have a very hard time holding on to this because the paper keeps moving. Let's see if I can do it like this with my elbow. Begins running out of H? Yes. Temperature drops? Yes. Gravity collapses? Yes. Core temperature goes back up? Yes. Is it a red supergiant? Absolutely. Does it run out of hydrogen? Finally. Does it switch to helium? You bet. Helium flashes? Yes, several. Switches to other elements? Yes. I already told you carbon, neon, oxygen, silicon. Okay? Then fusion finally stops, and it's going to get real bad now. Gravity crushes it very quickly. It implodes. You have a supernova. An even bigger supernova, because this is an even bigger star with 25 times more stuff than the sun has. Now, what you get here is the atoms are ripped apart again, but there's more atoms. And the protons and electrons are blown away. And the neutrons are pulled back together by gravity. But this is the coolest, weirdest thing of all. There are so many more neutrons. Okay? I'm going to pause and write it out because I have to put this camera down. I'll be right back. Here we go. Dramatic ending. There are so many more neutrons involved in this implosion. And they hit each other so hard. They hit with so much momentum, they can't stop collapsing into each other. And they rip a hole in the universe, and they disappear, and they start pulling in other stuff behind them. You just made a black hole. That's what is happening here. Now I'm going to draw that up here like this. Okay. There are so many more neutrons, and they hit each other so hard, they collapse into each other forever. I'm going to pause again. All right, I'm back. I wrote, they collapse into each other forever. And forever is not a really long time. It doesn't have an end. They just keep going. We don't know where that stuff goes. Apparently it goes into a different universe. Okay? You get a black hole. Even light can't get away from it. That's why it's called a black hole. Okay? You can't see a black hole. You can't measure a black hole. It has no size. It's infinitely small. Stuff getting sucked into it. You're like, well, yeah, but how do we even know they're real? We found them, but you can't see them. The first one we found was called Cygnus X1, and the X is a clue. we found a star, a big star, that was orbiting something very heavy but invisible. It was just going around and around and around. Like, stars don't usually do this. Like, what is that all about? And then we detected X-rays coming from the area right next to that star. It's like, what is going on? And what it was a great big blue supergiant that was being eaten alive. Its partner had turned into a black hole and was sucking the outer layers of the blue supergiant into it. And as the gases are going around and around and around, like stuff going down a drain, as they go around the black hole faster, 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 they start a death scream of X-rays, like, I don't want to die. And we were detecting those X-rays. If the X-rays get out before the stuff goes into the black hole, some X-rays can get away. They have enough energy, they can get away. Regular, other kinds of light cannot get away from a black hole. It's wild. Okay? Now, I'm going to pause this and get a couple of pictures up, and I'll show you what a planetary nebula looks like and what Cygnus X1 would look like if you could see X-rays in a black hole. I'm going to pause. All right. This is a picture of a planetary nebula, the most famous one, called the Ring Nebula. And that little star there in the middle is the new white dwarf that's going to run off the new hydrogen it got. And on all those colorful layers, that's the star's outer layers being blasted off into space. Okay, now I'm going to show you a picture of Cygnus X1, what it would look like. The big blue-white star being eaten alive as stuff is getting sucked into the black hole. Can you see the black hole right there? Trick question. No, you can't. That black area is where the black hole is, but technically the black hole is infinitely small in the center of that. It has no size. And this jet here coming out both ways is X-ray death screams of the gases that are getting sucked down into their death and disappearing. You gotta admit that's cool.